so really quick. So Brendan, as I was walking around, said, hey, when did we learn power equals force times velocity, which we did. But so I think I didn't stress something, and this problem really gets at an important idea, which is this. So we learned that to calculate the instantaneous power, it's, and I think I just said force times velocity.
Yeah.
All right. And hopefully, I believe I said, what's up? What's wrong, Margaret? Okay. It's in the notes, yes?
Yeah.
Right? And so we talked about the fact that technically speaking, it's a dot product. Okay? And so what that means is, if you want to calculate that, it's force times velocity times the cosine of the angle between those two things. Okay? Because remember, this all stems from the fact that work is force times displacement as a dot product, right? Follow? All right. So, anytime you've got a thing going in a circle, that motion is maintained by centripetal force, right? So, if I've got an object that's going in a circle, suppose it's going around, what is that, counterclockwise, right? Or no, why am I dumb? Yeah, counterclockwise. So, everybody point for me. When it gets right here, what direction is the velocity in? The velocity. The velocity vector would point this way, right? And the force providing the circular motion would point this way, right? So what's the angle between those? 90. Okay. So is this centripetal force doing either work or generating power? No, because this angle here is going to be 90. Cosine of 90 is 0. In other words, there's no force in the direction of the motion. Okay? So, anytime your force is perpendicular to your motion, there's no work and therefore also no power. Cool? All right, so that was that one. On number 2, did everybody understand that you just had to do dot products here? Right? So how do you do a dot product when it's written in unit vector notation? Sure, we got that? Multiply component-wise and then add them, right? So for A, for example, if you wanted to find your power, it's force dot product velocity, right? So 6i minus 20j dotted with negative 4i. So when you multiply, you're going to get, let's see, your I components are going to give you negative 24, right? What do I do with the j component? It's 0, right? Because this is really plus 0j, right? So you get negative 24 joules for that one. Or, sorry, watts. Watts. Okay, so that was all you had to do with that, was calculate the power for the three of them by doing that dot product and then rank them. Everybody good up to there? Any problems? Those of you that were asking about the concept-y stuff, everybody cool with that? Cool. Number 3, I realized somebody came in this morning and was working on this with me, and I realized that I wasn't super happy with the way this is worded. So it says compute the work done by the force in the first second. And it doesn't specify whether it wants instantaneous or average. But there's really only one possible solution here, right? Because the first second isn't describing an instant. It's describing an interval, right? So really, the only thing you could possibly do is calculate the average power. Or, I'm sorry, the average work. Oh, wait. Work is change in energy. I'm an idiot. No, it's worded perfectly fine. So you just find the change in energy. Sorry.
Yeah.
Oh, yeah.
Sorry, it's fine. Okay. And then for D, to compute the instantaneous power, that's where you got to do force times velocity.
Oh.
Does that make sense?
Wait.
Sabo, you good?
You do force 5 times VF, which is yourself.
Correct.
Okay.
And you can do that either using kinematics or conservation, or energy, by finding the kinetic energy. Carly, you good?
Yeah, I just didn't even see the question. So
Gotcha. Okay, so everybody's happy with 3? Okay, let's see. Was 4 on my list? It wasn't, surprisingly.
Oh, I needed 4.
let me hit 7, 9, 10, and 11, and then I'll come back to 4. Is that cool?
Yeah.
So,
Oh, you know what? Actually, let me talk about 4A because that's a concept
yeah.
thing.
Okay,
Okay.
I got 4A.
Please, just no, skip.
All right, we've spent this much time on it. Let's just finish it. All right. So for 9A, so here's the idea. It says a skier's pulled by a tow rope up a frictionless ski slope. Do they even have tow ropes anymore?
Yes.
I've been
On the
skiing
bunny
a
hill.
bazillion years. So a skier's pulled by a tow rope up a frictionless ski slope that makes an angle of 12 degrees with the horizontal line. So here's this. Here's your skier. Put a hat on. It's cold out. It's a little pom-pom hat. Yeah. I'm pretty happy with that drawing. Oh, but you got to hold your poles, which is always on the. There you go. All right. So there he goes. All right. Good. So let's see. So what forces are going to be acting on our dude, you guys? Gravity and the tow rope, right? So there's the force of the rope and FG parallel, really, right? Is all I care about. Because it's frictionless, so I don't need to worry about blah, 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 blah. All right, everybody good with that? All right, so let's see, what do we know? We know that he's going up the slope at a constant speed of 1 meter a second. Why do you think it's important that the speed here is constant? Zero acceleration. Relate that to energy, you guys. Net force is 0, so there's no change in kinetic energy. There's no change in kinetic energy because the velocity is constant, right? But that tells us that my change in kinetic energy and my net work are both 0. So that means these two forces need to be equal, right? So that means the work done by the rope is equal to the work done by gravity, right? With opposite signs, right? All right, let's see, what else do we know? It says the force of the rope does 900 joules of work on the skier. So the work done by the rope is 900 joules as it goes 8 meters up the incline. A, if the rope moved with a constant speed of 2 meters a second, how much work would the force of the rope do? It would still be the same, right? Because you'd still have to have, so, all right, so this is my work done by non-conservative forces, right? Okay, so in this problem, look, my kinetic energy isn't changing. So why does the rope have to do work? If there's no change in kinetic energy, what sort of function does the work of the rope serve? That's a bad sentence. What do you guys got? In terms of energy, why is the work from the rope important? You still need to go up. You need to change gravitational potential energy, right? So this is my change in total energy, which for this problem is the change in GPE, right? Does that make sense? So in part A, increasing the velocity doesn't change any of this, right? You're still going at a constant velocity, so your kinetic energy is not going to change. So you're still going to need just as much GPE to get up the slope, which means the same work from the rope. Cool? So that's part A. Everybody good then? Okay. Part B, at what rate is the force of the rope doing work? So first of all, the rate at which work is done. What's the physics word for that, you guys? Power, right? So we're trying to find the power when the velocity is 1. Well, we got to find the force of the rope, right? All right, so there's 2 ways you can do this. Oh, no, because we don't know the mass, so we can't find FG parallel that way. So does anybody see an easy way to find the force of the rope? What do you got here?
So it tells you that the rope does 900 joules of work over 8 meters.
Cool.
So you just do the motion.
So you're telling me that the work of the rope is 900 joules. Force of the rope we don't know, but we do know that the displacement is 8 meters, right? So that means that the force of the rope is, what is that, 112.5 newtons? Is that right? I did that in my head.
Yeah.
Cool? Yeah? Oh, really good question. Somebody want to take a stab at it? Sure, we got.
So it's because like it tells you that the skier like moves a distance of 8 meters up the incline, so you know that the 8 meters is like is the distance of the incline, right?
Yep.
So then the force is like it doesn't tell you that the force is like at an angle. So like I guess I just like because it didn't say that it was a different angle, I just assumed that it was like the force was parallel to the motion.
Yeah.
It says it's parallel to.
Yeah. So here's the deal. So this equation here, which is actually left here from honors, but so work is force times displacement times the cosine of theta, and similarly power is force times velocity times the cosine of theta. That theta represents, for the work equation, it's the angle between these two vectors. And similarly for power, it's the angle between those two vectors. Cool? Everybody good?
Is that the answer for B?
So to do part B, so we've got our force from the rope, right? So now we got to find the power from the rope, right? So the power from the rope should be force of rope dot product with the velocity,
Which is 1.
which is 1. Cool? So, and this is, these answers, I need to tweak them. Those are rounded off to sig digs. So that's why the answers are off by a scotch. So make a note of this. This should really be 112.5. And this one then is going to be, what, 225?
Yeah.
Is that by any chance the answer that I had on the back?
No.
No.
No? Okay. Sorry. All right. Everybody good with 4?
What about C?
So the force of the rope is constant. So again, it's just force times velocity. You know the force is 125, and your velocity is 2. So you just multiply. Good. Everybody good? Okay, cool. So that was 1 through 4 real quick.